So this title might actually seem really odd for this community, because of course, if you look at our program, every single paper here is a collaboration, right? We collaborate with our students or our advisors, we collaborate with our peers, we collaborate with our colleagues. So of course we collaborate. So like, Margo, what the heck are you talking about? And so what I want to talk about is a little bit about how to make your collaborations even more impactful. And I want to encourage you to think about collaborations with people outside this community. It doesn't have to be machine learning people. We will talk about that because like it's 2023. Hopefully it'll be a little different than a lot of the ML talks. But I just want to encourage people to think about the superpowers that this community has in making things better. And we have those superpowers in lots of different areas. And everybody in this room also has their unique superpower that they bring to the table. And in my mind, the reason for collaboration is when you can find different people with different superpowers and sort of blend them together. And so I'm going to try to give you an example of mostly like how that changed my life in a really great way, I think, and encourage you to do the same. So that's the goal for today. And so we're going to cover a few different things that will include superpowers, because who doesn't like superheroes? Imposter syndrome, because, I don't know, I'm going to guess that almost everyone in this room has suffered from imposter syndrome at some point. I think students tend to think that they're the only ones who suffer from it. But if I recall, at the doctoral workshop on Monday, maybe one of my esteemed colleagues even admitted that he too sometimes wakes up asking like, oh my God, what am I doing here? So we'll talk a little bit about that. I actually think collaboration is a great cure for imposter syndrome. And then at some point, we'll talk about some systems and some machine learning, and even that will be somewhat controversial, I hope. And if you don't like that, we should definitely talk about cats, because all the work we've done has made it easier for people to view cute cat videos or find pictures of cats. And I just want to give a call out to Meta that my Facebook feed now, all the reels are cats. So I'm not sure who won. Either they won or I won, but it's all good. All right, so if you have ever written a paper with me, and my students are all going to roll their eyes right now, you will know that I believe in fairy tales, that every good piece of work, whether it's a paper or a talk, is really a fairy tale. So I'm going to start with a fairy tale, and all fairy tales start with once upon a time. So once upon a time, I was at Harvard, and Cynthia Rudin, who was at Duke, came to give a talk. And I thought it was a really interesting talk. I enjoyed it a great deal. And when we met, I said, oh, I really liked your talk. And she wistfully said, you know, if only could we make this algorithm scale. So she had presented a Markov chain Monte Carlo algorithm for building rule lists. A rule list is basically a cascading if-then-else statement, right? So if it's raining, I'll carry an umbrella. Else, if it's not raining but it's cloudy, I'll carry an umbrella. Else, if it's Koblenz, I'll carry an umbrella. Else, if it's Vancouver, I'll carry an, else I won't carry an umbrella. So it turns out that you can build like real machine learning models that are rule lists, and they're very easily understandable. And she had presented like the state-of-the-art algorithm to do this, but it didn't scale. And I was like, hey, I just had a student who finished some work on trying to make Markov chain Monte Carlo scale. So like maybe we should work together. And this sounded really good. And we did work together, but every fairy tale has a villain. And the villain was that like what I knew about rule lists, I had just learned in the last minute and a half. And I just shared that with you. So now you know everything I knew about rule lists. The other thing was like a bigger problem, which was like, I liked your talk, I really enjoyed it. I did not understand any of the math in it, and there was a lot of math. And the bigger problem was that I really, really hated saying like, I don't understand what you're talking about, even though there were lots of pieces that I didn't understand. And so of course, this is what we know as imposter syndrome, right? And a lot of times it holds us back. But in fact, what that holding back does is it really puts you in a cage. And so I'd like to propose that the hero that can vanquish the imposter syndrome villain is actually what I like to call the stupid question. Now, colleagues have told me that it's not actually a stupid question, it's a question of naivete, right? So if somebody says something that you don't know a lot about, and you kind of want to say, like, I don't really understand that, but it's a little scary to do that. And it's really scary when we're all in the same community because you feel like I should know this. And it turns out the more senior you get, the more often you feel like, oh, clearly I should know this because, like, I'm senior, right? But in fact, there are many, many things that none of us know, or that for each of us, there are many things we don't know. And it's totally okay to do that. And in some ways, collaborating with somebody who's not in your area of expertise gives you this freedom to say, like, I don't understand that, because you're not expected to. So one of the cures for imposter syndrome is like broadening your collaborations with people who have really different areas of expertise. So, you know, what this would look like with me and Cynthia is that I would work up the courage to say, like, I don't understand that. And she would say, well, if you don't understand it, let me explain it again. It was like, oh, that was kind of nice. And then she'd explain it again, and I'd say, could you do that once more and like maybe use really small words? And she'd like say, sure, we could do that. And so we developed this incredibly trusting relationship where either of us could ask these questions of naivete, and it didn't like jeopardize our feelings of like who we were or what we knew. And that was really cool. And so what happened was, we could like bounce back and forth between our two areas of expertise and do things that neither one of us could have done alone. So there was this one day that stands out in my mind where she and her student and I were sitting in her office with screen on the board, and we were doing a code review, which, oh, by the way, ML people had never done before. Okay, not just Cynthia, like this is code review? What's that? Turns out there are lots of superpowers we could share. So we're doing a code review. And part of the ways that we ended up making stuff faster is that we would try to reuse computation where possible, and we would try to cache computation. And this was like a whole new thing for this kind of work. And so I would look at the code, and like, this will seem obvious to people in this community, but I'd look at code and say, like, we're doing a computation in the loop, but isn't that computation the same every time? And sometimes it would be, and sometimes it wouldn't be, because like there were some subtle changes in these Python data frames. But when there was, you know, and you know, Cynthia would say, no, it doesn't change sometimes. And I'd go, cool, like that means we can compute incrementally and like reuse computations. And then she might say, like, well, what does that mean? And it's like, well, if we keep track of just the right information, we can know that we don't have to recompute things, or we could compute things incrementally and everything will go faster. And as soon as I explained that, like in the next block of code, she's like, wait a minute, we can do the same thing here. And so the process just went back and forth and back and forth, and in a 2-hour code review, we sped up code by 2 orders of magnitude. Now, you might say, well, of course, the code was badly written. But let me tell you, in most other project in this field, like no one ever would have taken the time to look at that. And it wouldn't have happened if we hadn't been working on the project together. So that was kind of cool, and that really made both of us feel like there's something really good happening here. And so we have continued a 10-year collaboration. You know, the one constant when I first moved to UBC and knew nobody else in the world there was that Cynthia and I met once a week with our students, and we made progress. Now, there have been many other collaborators since then, and some of them are in systems, but many are not. And collaboration is great, whether it's with people close to your area or far away. But I'd like to encourage us also to think about collaboration with people further away, because I think that actually brings a richness that collaborating with people who already speak our language doesn't always bring. All right, so with that as sort of a preface, what am I really here to talk about? So in this work with Cynthia, I've learned a bunch of really interesting things about machine learning. And some of them I think have profound relationship to the work we do in systems and how we should be thinking about how we can use machine learning too. And so that's what I want to talk about today. So how do machine learning and systems work together? And broadly, there's kind of 2 ways that we do this, right? One is that we take a machine learning system and we sprinkle magic systems dust on it and we make stuff run faster, right? And that's clearly a good thing to do and a good contribution. There's another way we use machine learning, which is that we take a slow system and we sprinkle magic learning pixie dust on it, and then the system runs faster. I want to talk about this second kind of work for today, even though most of the papers we saw earlier were really in that first category. So how do we do this? What kind of frameworks do we use? Well, you know, we look at our system, and I think much to our dismay, the first thing we think about is like, well, clearly we must use a deep neural network because like, they're so useful, that must be the right answer. I'm not so sure about that. We might think that reinforcement learning is a great solution in our space. Maybe it is. But I want to say, you know what? In systems, we often try to find really simple solutions to complex problems. And so I think we should try to find simple models to solve complex problems. And by simple, I mean interpretable. Now, let me take a brief digression here. You will hear the term explainable AI and interpretable AI, and most people think they mean the same thing, and they don't. So what explainable AI means is that you have some black box model, think neural network, it makes a prediction, and what you want to then do is kind of reverse engineer why you think it makes that prediction. So it's a very indirect path to explaining what's happening. In contrast, an interpretable model is one that I can like print out on an index card and hand to you, and you can read it and you can go, oh yeah, I know exactly what it's doing, right? Or if a decision is being made that is going to affect your life, like whether you get to have a mortgage to buy a home, you can look at why you were denied that mortgage and know exactly why you were denied and maybe what things you can change to not be denied in the future. So they're really inherently different approaches. And so I'm going to focus a lot on interpretable models because that's what I do. And that's what I think everybody should do. Or not everybody, at least some of you. All right. So the way to think about this is that there are actually two really different kinds of problems in machine learning. So the ones we hear a lot about, where neural networks have had great success, right? Things like image recognition, or speech recognition, or translation, or all these apps where there's been really fundamental breakthroughs thanks to progress in deep learning, which, oh, by the way, is thanks to colleagues in architecture and systems. So, yay, we enabled that revolution. And it's had huge effect. But these problems have two things that really make them unique. So one is that like there is a correct answer to these problems, right? A cat is either in the picture or it's not in the picture, right? If I ask Alexa something, there's a very specific thing I said and we want the answer to be to that question. Secondly, the individual features in these problems don't carry a lot of meaning, right? A single pixel, not super helpful. Even a single word in a sentence, not super helpful. So these are sort of two characteristics of the kinds of problems where we found that deep learning has been fantastic. But it turns out there's a whole other set of problems, particularly when we talk about high-stakes decision making. So I'm thinking about things like medical diagnosis, or granting people loans, or deciding who gets out of jail. Right? These are decisions that have enormous impact on people's lives, and they have two features that are very different from those previous problems. In particular, the answers are actually probabilistic. We don't know the future, and so we don't know what the right answer is. So we're trying to make a good guess at what the right answer might be. And secondly, the features are often quite meaningful. Think about how you collect metrics from your computer systems when you want to improve performance. Do you collect random things, or do you collect things that you believe are meaningfully correlated with performance? Right? I'm going to guess that you try to collect things that actually have real meaning. So if I think about the kinds of problems we have, and I'm thinking about things like resource allocation, or picking appropriate VM container sizes for particular workloads, identifying stragglers, making memory predictions, right? All these problems, I would claim, look a lot more like these problems, and so we should be taking a tip in techniques from sort of what works in this space. So that's sort of the heretical place I want to start. Now, intuitively, we might think, well, these are hard problems, so of course we should build increasingly more complex models. But it turns out that that's not necessarily the right approach. In problems where the answers are probabilistic and the features are meaningful, and so problems like these, and for us, problems like these, oops, I'm one click behind, it turns out that increasingly complex models actually don't help. right? So we're in a space where our answers are probabilistic and the features are meaningful. And it turns out that deep learning actually doesn't help in this space. There is no trade-off between giving you a model that is interpretable and sacrificing accuracy. And most of the time you hear that there's absolutely a trade-off, you can't have both. But for this class of problems, it turns out that you can have both. So, there's one small detail here. You have to solve an NP-hard problem to do this. Small details. We'll come to that. So here's what I want to do for the rest of the talk. I want to give you an example of how people thought this was impossible and you have this trade-off. And then I'm going to present like one way of finding these simple models, which happens to be like the first thing, well, the nth thing that Cynthia and I did together. And then I want to talk about like why this is actually true. Because there's some really interesting theory behind the existence of these simple models. And then I'm going to put some challenges to you, some of which fall in this space and some of which might veer away, but I still think are really important problems that we should solve in this sort of space between systems and ML. All right, so it turns out that a bunch of years ago, FICO, which is the major credit scoring agency in the US, got together with folks like you might have heard of, I don't know, Google, MIT, Oxford, Berkeley, a bunch of other people like that, and they launched something called the Explainable ML Challenge. And they released a data set and asked people to build black box models to predict whether someone would default on a loan and then explain the prediction. Now, in the posing of this problem, there is an implicit assumption that you had to build a black box model. And so that's what everybody did. But it turns out that was not true. So this is a machine learning model. It's a general additive model. The way you use it is that you look at a feature. Let's say this, whoops, get back here, right? So, okay, hold on, my screen's now doing something really awful. Where is my presenter view? Here it is. Okay, so what you do is you look at something like your external risk score, and let's say yours is 20, then you go up here and you get a certain number of points. So there are 11 features here. For any given sample, you just look up the feature in each of the 11, you look up your value for the 11 different features, you add it together, and now you get a score that is a risk score for how likely you are to default on your loan. Okay? So if I look at a sample, you have a good idea where the different pieces of that risk score are coming from. Turns out you can build lots of models that do as well as the best black box models. So here's another one. This is a decision tree. And so you start at the root and you say, is your external risk estimate less than 70? And if it is, then you're going to default on a loan, it turns out. Who knew? If it's not, then we go and we ask a bunch of other questions. And, we produced the general additive model, which is the best model you can do on the FICO data set in like 4 seconds. And it achieves the accuracy of like all the black box models. Similarly, I think this tree took us a little bit longer, but it too gives you the same predictions. So, turns out there's actually a reason why a lot of these model classes give you the same predictions, or why that's a symptom that you can find a simple model. And we're going to come back to that at the end. What I'm going to do now is say, so how is it that we actually solve this NP-hard problem? Because that seems like a stupid thing to try to do on a laptop. So this is work done with a bunch of students at Duke, a bunch of students at UBC, my postdoc, Reto Ackerman. Yes, he's on the job market. You want to hire him, but so do I. We can arm wrestle later. This is called the algorithm that we developed. There's a couple of steps along the way, but it's ultimately called GHOST. It stands for General Optimal Sparse Decision Trees. And it means we get to have cute little ghost logos. So here's the problem we want to solve. Here's a data set. Find the decision tree that is best, I'll define best in a minute, for this data set. Now, great, we're just going to search the whole search space. No big deal. For realistic problems, the search space is really, really big. So the question is there a way we could efficiently search that space? Or more precisely, how can we prune this space so that we don't have to search large portions of it? And so that is exactly what we want to do, is that we want to use tight mathematical bounds to identify pieces of the search space that can't possibly have the best solution. Because if you remove those, then you only have to solve the problems actually in the part of the search space which you know might contain the optimal solution. And then once you've found that optimal solution, we're going to give you a certificate of optimality that says this is the best you can do. All right, so how do we do this? This is an optimization problem. So an optimization problem needs an objective function. So these are the kinds of things that used to make me like tense up, and now I can explain to you calmly, right? There's two parts to this. The first part is just the misclassification error. So for each sample in our data set, we have n samples. Did we predict it right or wrong? Okay, you could think of this as an accuracy, or in some sense, this is actually the error. How many did, what fraction of the data set did we get wrong? Now we're going to add a sparsity penalty, because if I give you a decision tree with 1 million leaves, it might predict every one of the 1 million data points correctly, but it wouldn't actually be very interpretable. So what we want to do is we want to be as accurate as we can with a sparse model that has very few leaves, because then you can actually interpret it. And the sparser the model, the better it will generalize to data that we haven't seen yet. So in this case, we're going to optimize for accuracy, because we have misclassification as our first term. You could change that term and optimize for other things, like balanced accuracy, or weighted accuracy, or AUC, or any function that for this algorithm is additive. And because of the way we implement this, the loss function has to be additive. So how do we implement this? We call dynamic programming with bounds. Now, a bunch of the techniques that I'm talking about here, you're going to say, well, duh, that's obvious. Like, that's really simple. And we think like that. That is one of the superpowers of this community, is that we can think about the right data structures, the right algorithm, the way to save computation. It's part of our community's DNA. It is not necessarily part of the DNA of other communities. So the message you should take away is, whoa, like I can think of simple algorithms and data structures that could make stuff better, and then go find people who need you to help them do that. All right, so we're going to start with the full data set. And the way to read these pictures is that the dots represent samples, and the blue dots represent, let's say we're going to predict true, and the yellow predict false. We can just think of it as predicting blue and yellow. And for any given problem, the color of the box is what we would predict if we just had to make a prediction given this data set. Right, so in this case, we have 6 yellow dots, we have 11 blue ones, and so we would predict blue, and our accuracy would be about 62%. All right, so, when you consider a feature, so let's imagine that this data set has 3 features, we could split on either one of those features. We could take the data set, and the 2 leaves of the tree could go to it, yeah. You could create a tree on each of these 3 features. And so we might get splits that look like that. And then each of those you could split again, and you could keep going, except some of these problems you really wouldn't want to split. So if you look at this problem, we have a blue box and all the dots are blue. So here's a case where we can predict this part of the problem with 100% accuracy. So we wouldn't even bother splitting that again. It would be silly. We would split other things. The other thing you might notice, or you might not because there's a lot of dots on the screen, is that you can generate identical subproblems through different paths in the tree. That suggests a way that maybe we could save computation. Like if we could identify that we're solving the same problem we've already solved, think of this as memoization, right? If we could figure out a way to do memoization, then we could reuse computation, and wouldn't that be cool? So that's exactly what we're going to do. So if you look at how decision trees were constructed at the time we started doing this, and the field has moved since then because people have said, wow, you can build optimal trees, let's try to do that. So the way that you would do it in the past is they'd be mostly greedy heuristics. So you'd figure out what's the best split I can make at the root. And then you would make that split, and then you were stuck with it, and it would never change. And if you happened to make a bad decision, you were going to get a bad tree. What we do is we say, no, we're actually going to consider all the splits, and we're going to keep building out all these splits until we have this like huge collection of these subproblems, right? Now the beauty of these subproblems is that we can evaluate them independently, which also means in parallel, so that's cool. And more importantly, if we keep track of some information about these subproblems and where they came from, in Margo speak, you could think of it as their provenance, you can start to eliminate problems in this tree that cannot be part of any optimal tree. And so the idea is, as early as possible, we want to figure out places in this search space that just don't contain any good models. And if we can do that, then at the end of this, what we have is a graph of all the subproblems and how they relate to each other. And then you traverse the graph, you find the best model left in there, and you say, this is the best model we can do. All right, so that's kind of cool. So how do we actually make this work? There's two problems that you have to be able to answer. The first is, how do I identify identical subproblems so that I don't go do the same thing all over again? And then the second one is, what kind of state can I maintain with each problem so that I can A, prune the search space, and B, make as few computations as I can every time I'm computing the loss for a particular tree. Because what we're going to do is we're going to compute loss a lot. And so anything we can do to make that faster, total win. All right, so here's what we're going to do. So this was the same tree I showed you. And we're going to focus on splitting and following sort of the yellow boxes. So we're going to represent a data set as a bit vector. So in this case, we have 17 samples, so we have bit vectors of length 17. Yes, this means that if you have 1 million samples, you have bit vectors of length 1 million. Turns out you can do that, right? It's not necessarily how people think of this, but you can build really big bit vectors, and manipulating them can be really quick. And so when we split, we're going to create different bit vectors that when you OR them together, you got the parent from whom you split, and some of the bits go to each of the subproblems. Cool. So let's focus on the yellow box. Let's imagine that we do this split. And so we have this bit vector, and we're going to split again, and we get another bit vector. And then we might have other splits that we look at. So we're going to look at this one, and then we're going to get to this one. And you might remember I showed you that you could have duplicate subproblems, and sure enough, those two bit vectors are the same. So if we key our subproblems by these bit vectors or hashes of these bit vectors or whatever lookup you want, we can identify common subproblems. Cool. Instead of creating that subproblem, once we identify that it's a duplicate, we say, nope, we're not going to create it. But we're going to keep track of the fact that this subproblem now could be produced in two different ways. And depending on how it was produced, there will be different constraints about how much loss or how much inaccuracy this problem can tolerate. And so that is going to drive what information we want to keep for each subproblem. So this is a big box as a subproblem. It's keyed by this bit vector. And the first thing we're going to keep track of is something called the support, which is what fraction of the data set does this subproblem represent. So in this case, the number that are in this sample is 6. There are 17 total. And so this captures about 35% of the data set. So what that means is even if you were terrible at predicting this, it would introduce no more loss than 35%. In actuality, you should never do worse than 50%. So you can figure out like how bad could this node make things or how good could this node make things. The next thing we want to keep track of is an upper bound. So this is like, what's the worst loss we'll get from this part of the data set? And the worst loss happens if you just say we're never going to split this subproblem. We're going to just predict this subproblem. If from an accuracy point of view, you just pick the majority label. I'm always going to predict this one blue, or in our case, yellow, right? So here's our box. There are 6 points. 5 of them are yellow. Clearly, we would predict this yellow. Our error would be 1/6, and then we would add the sparsity. So we'd add a penalty for the leaf. Okay, so this says that if we did nothing else, this is the absolute worst error that you'd get, or the worst objective. Similarly, we want to keep track of the best objective you might get. So let's imagine that we were able to predict everything correctly. Then you should get no error. Turns out you can't always do that. And you're all looking at me going, wait a minute, why can't I just have a separate leaf for every sample? Well, because some samples have identical features and different predictions. So those are always going to end up in the same leaf. So if you pre-process the data and identify these equivalent point sets, you can actually derive a lower bound that you know any model you build is going to predict all these points one way, and some of them will be wrong. So that gives you a lower bound. Now, the lower bound and the upper bound are really local to a subproblem. So independent of where this subproblem appears in your graph of problems and relationships, this information tells you about that subproblem. But it turns out that you also know some things about your bounds based on who your parents are. And so we call the upper and lower bounds that are sort of imposed by your position in the tree upper and lower scope. So let's look at an example. So let's imagine that we have a parent problem here. And this particular problem, its upper bound is, 0.35. So that's the worst error we'll ever see. Okay, let's imagine that we've already figured out that if we split on a certain feature, one of the children, I'm going to call it the left one, the best it can possibly do is to produce a loss of 0.25. Well, what this means is that the other side of the tree, which you haven't yet computed, had better come in with a loss that is no bigger than 0.10, because if it's bigger than that, that's worse than just stopping splitting here. So what that means is that depending on who your parents are, you can tighten your bounds as you go, thus letting us prune the search space more effectively. So there's a couple of different ways that we're going to transmit information up and down the tree. So when we discover that, this bound can't be, the loss can't be more than 0.10, we're going to transmit the real loss back up to the parent. The parent might then know information it transmits up to its parent and go up the tree. But it also may now be able to change the information that it gave its other children, and so will also pass messages down the tree. So to a first approximation, this is a dynamic programming implementation that does a couple of things, right? It identifies duplicates, it maintains intermediate state to speed it up, and then it uses that information to propagate throughout all the subproblems we have so that we can throw them away as quickly as possible. And it turns out you can do this with lots of different models. So these are decision trees. You can have different objectives in the decision trees. We can have weights on the samples in the decision tree. We can build regression trees. All of those are essentially built from the same code base. And then there are other problems you can do. So you can do survival trees. This is like making a prediction about how long something is going to last. It's often used in medicine where the how long something is people. You can build scoring systems, right? These are just linear models with integer coefficients. And it turns out that for a huge class of problems, you can't do better than using all these simple models that are dirt simple to compute. Like once you have the model, computing it for any sample is really fast. And in most cases, you can actually build the optimal model really quickly. So you might be saying, like, this sounds too good to be true. Like, why could this possibly work? So it turns out, and let me just be clear, this is all work that Cynthia has done, and so I'm just going to channel the big picture here. But, for 20 years now, we've known that there is this thing called the Rashomon effect, which says that for most real-world problems, there are many, many, many models that describe the data equally well. So the goal isn't necessarily that you have to use any particular technique, it's that lots of techniques will do equally well. And it turns out that if you have a problem and you try a bunch of different learning techniques, so you tune your gradient-boosted decision trees, and you tune your support vector machines, and then you say, oh, forget it, I'm going to build a neural network. And if you tried lots of different model classes, and you get roughly the same objective, this is actually a huge indication that the Rashomon set is really big, and in particular, it's really big with respect to the whole search space, the whole space of models. And when that's the case, there is very likely to be a simple interpretable model that'll explain it. So let me just make that visually apparent. So the rectangle here represents the entire universe of all models you might try to use on the data. And the red dots are simple models. And there's not a lot of them, but they're kind of scattered throughout the space. The cloud is the Rashomon set, this set of all the good models. If that is relatively large with respect to the space, and it turns out it is in a lot of these problems, then in fact there is highly likely to be a simple model in that space. And from a systems perspective, if there's a simple model, why would you choose a complex one that doesn't do any better? All right, so knowing that this Rashomon set exists is one thing. Finding it is entirely a second thing. So at some point, Cynthia said to me, let's find the set of all decision trees in the Rashomon set. I'm like, are you crazy? This seemed preposterous to me because there were potentially hundreds of thousands or millions of models, and this seemed totally crazy. And she's like, no, I actually think we can do this. I'm like, really? So here's how you do it. You take an algorithm that produces an optimal model. In this case, let's imagine that it's Ghost. I keep juggling back and forth here. So you take your input, you put it into Ghost, and Ghost comes back and says, ooh, okay, the best model I can do is, 75.9%. And then you say, well, I would like all the models that are within 0.01% of optimal. Because all algorithms just give you one model. What would happen if I could get all the models that are very close to optimal? Well, let's see. So you take the best tree, you take what we call the Rashomon bound, so how far away from optimal are you willing to go, you give it the data set, you basically feed it into the exact same algorithm that computed your optimal tree with like 1 or 2 configuration changes, and out pops thousands, hundreds of thousands, or millions of trees, depending on your data set. Now think about that just for a minute. There are 1 million models that will do equally well on this sort of data. That's kind of awesome. It's also a little intimidating. So like, what do you do with 1 million models? Well, what you do is you go find yourself, whoops, we skipped a slide. Okay, you go find yourself a really, really good viz person. Okay? And so this interface was done by Jay Wong from Georgia Tech. But this was a side project, right? This is not like a big paper for him. This was a short paper at InfoViz, right? So we presented the problem to him. He came back the first week and showed us this picture, which I'll explain in a minute. And he then met with us once a week for about 3 months. And from my impression, he would spend a couple hours tweaking the implementation. And at the end of the month, we had this. So let me show you what this is doing. So this is showing you all the decision trees for the Compass recidivism data set, where the prediction problem is which people will commit a crime and end up back in jail in the next 2 years. So you look at the innermost circle, and this is all the possible features that we might split the root on. And you look at this and go, wow, number of prior crimes greater than 3 seems to be like a really important feature. So let's look only at the trees that start with that as the root. So now we're looking at a subset of the trees. And if you click on any of these gray boxes, you get to actually see the tree. And maybe you look at this one and go, ooh, I like that. So you can like save it as a favorite. You can leave a little note on it, like, oh, this is the one during the talk. And you can sort of look all over the space and see lots of different trees. If you don't like them, you can just make them go away. And then you might say, people talk about fairness constraints and not wanting to use some features. So maybe I want to bound the space a little more. Oh, gender, that seems like a really sensitive feature. Let's make that go away. What? I can't see it. Oh, wait, it's not moving. Oh my God, okay, it's moving here. All right, hold on. Let's see if I can figure out where. Ooh, I have another screen. Let's see. Okay, apologies. Sorry I didn't notice. Feel free to scream at me. It's not that one. All right, let me get rid of these ones that it's not. Not that I've done this talk a bunch of times and practiced it or anything. We're just going to make timber treks go away. How about now? Nope. All right, I actually did try to check this before. Not that one. Okay, this is really annoying. Not this one. All right, what happens if I do this? Okay. All right. Oh, this is going to be super fun. Okay, I have to drive this screen. All right. Okay, now you get to see, like, you know, Margo's eye-hand coordination at its finest. All right. Let me start again. Pretend we didn't do any of that. This is the space of all the decision trees in this data set. If you click on one of the gray boxes, you get to see little trees pop up. Since I have maximized the screen, I can't actually grab that one. So we'll grab a couple of others. There we go. I can move this one. Cool. So I can say that I like it, and I can set the little heart. I can leave a little note and say this is a tree from the talk. I can pick another tree and say I don't like that at all. So I can now actually start to look at random models, but I still have a lot of models to choose from. So what else can I do? Well, I look at the middle here, and it's like most of the models have this feature. So let's look at the models that have that as the root feature. All right, we've just reduced the set. I might look at some of the others and say, let's try one of these, like, what if you have, like, no juvenile crimes? Like, that seems like maybe an important thing. So let's look at those trees. And now we have, like, a manageable number, and I can, again, look at individual trees, and this all works. But then I might say, you know, some features are really sensitive, and I might want to include those in models. So let's look at the features I have. And it's like prior crimes, yeah, age, ooh. Gender seems like a feature I don't want to consider. Let's not use that in any of the trees. So I've just eliminated that from all the trees. So you put this in front of an expert, and they can kind of get a sense for which of the features matters. Oh, but wait, we don't actually need people to get a sense. We've got the whole set. We can actually compute how important each feature is among all the good models. So one of the things the folks try to do in explainable ML is they look at a particular model and they say, how important is each feature in that model? We can ask a fundamentally deeper question, which is, how important is each feature in all the good models? And then you could try to pick your trees that actually maximize use of those features, for example, right? Or in the medical domain, what we find is that we put the first model in front of a doctor and they're like, oh no, we could never use that. And you say, why? And it's like, well, we don't like this feature. You say, okay, you know, navigate through some other models and pick one you like better. So as systems people, right, so now you have not one model that most algorithms give you, you have all the good models. And now you can start to search through it and pick the ones that you like, the ones whose features are really easy to compute. Like, wouldn't that be nice? Right? You don't even have to compute the other features that aren't in your model. So it gives you a lot of flexibility. All right, now let's see if I can go back to the slides. In fact, let's just make that go away. And now we're back at the slides, in theory, if I can get my mouse back. Where's the mouse? Nope. There's the mouse. All right, cool. So what are the implications for us? Right, the implications for us is that there are lots of different kinds of simple models. So there are things like decision trees, which I talked about now, but there are also things like general additive models. There are things like scoring systems. Scoring systems are great because they usually have cute acronyms, so you can just memorize all the features. How many of you have ever heard of an APGAR score? Yeah, if you have kids, you've heard of it, right? This is actually just a scoring system. APGAR is somebody's intuition, right? Who knows what you could do if you had all the data? Anyway, so you can pick models that actually make sense for whatever that means. Implementing these models, like actually using them, is super trivial. They are almost instantaneous to compute, and training them actually isn't all that hard. So we have now solved all the problems in systems, and so let's figure out what other problems we can solve. And so this is really about reaching out beyond the systems community to use our superpowers to solve other people's problems. So, how do you know that your machine learning model is correct? These are stochastic programs. We all know how hard it is to debug them, and we've dedicated like years and years and years to developing debugging techniques. The machine learning community hasn't done that. So when I started working in this space and sort of understanding the standards, I was a bit appalled. And so I came up with these two hypotheses, and I was hoping that all my colleagues in ML would tell me that I was like cynical and I was wrong, and here's why. And I was really looking for that answer. So here was hypothesis number one. Any paper that has an algorithm and an implementation, they don't match. And every single ML person I have said this to looks at me and nods. Goes, oh yeah. I'm like, beg pardon? and they're totally fine with that. So I thought, okay, if that one didn't make them just kill me, let's try hypothesis number two. There are a ton of ML papers out there that claim techniques that work, but in fact they don't. They just have bugs that make it look like they work. And they're like, yep. And I look like the deer in the headlights, and I'm like, really? Do you not care about this? Oh, if the results look good, that's all we care about. And I start to twitch. So we tend not to accept results like that. Like, I do think we have that algorithm problem too, and I'll give you a generalization of that in a minute, or maybe a specific instance of it. But I think this is actually a huge area. Like, how do you debug these programs? So we have tried to debug the programs. It's really hard. We have not had time to develop tools to do it. We do a lot of brute force debugging. And I see Reto probably nodding somewhere. It's really hard. So I think we could actually make this field more efficient by solving that problem than a lot of the performance optimizations that we all do. Here's another problem that I worry about a lot. My ML colleagues tell me this is a really, really hard problem, so we're good at really, really hard problems. So imagine that you train a model on a data distribution that looks like this. And then you start to use the model on a data distribution that looks like this, right? And if you can't fathom what this means, imagine that we train on a data set that has people of only one ethnicity, and then we try to use that data set on people who look very different. Your predictions might not be what you want. So how do we detect that this is actually happening? And what makes this problem particularly hard is that we know that models have sort of drift over time, and we want to adapt them. And so the question really boils down to, how do you disambiguate real drift that's happening over time and for which you want to tweak the models from like asking an existing model to do something that is just totally out of distribution? So my colleagues who I want to work with me on this tell me it's really hard, and we regularly talk about it, and we've never had nerve to actually try it. But you folks have way better ideas than I do, so somebody here can solve that one. And now here's my favorite problem that I would really like you all to solve. It's more of a PLOS problem, quite honestly. It's not exactly a systems problem, but I think it is a huge problem in machine learning. So what does the workflow look like to build like a new model or a new implementation of a model? So usually you sit down and you write a bunch of math. And then, of course, you render that math into LaTeX. Is this a lossless process? No. Okay, so there's a lossy process. So after you do that, then you feel pretty good, like you have an idea, and so you code it up in Python. Cool. That's a lossy process too. And then you run some experiments, and then sometimes the experiments show that maybe it's not right, so you fix the Python, okay. And at some point, maybe you feel like you've made real progress, and maybe you learned something new, so you write some more math, or if you're crazy like us, you often re-implement the whole system in C++ because fast. And yeah, there are other languages we could use. This just happens to be where we started. And then you run some more experiments, and then maybe you go back to the C++, maybe you write some more math, maybe you go write the paper. When this is all done, what is the probability that the math is the same as the Python, is the same as the C++, is the same as the paper? Okay? This is one of these probabilistic prediction problems. I don't need an optimal decision tree. The probability is 0. And nobody seems to care. Right? And we have some of these problems, but it's worse in this community. Like, this literally keeps me up at night. It makes me I torture my graduate students and sort of like, we have to rerun this test. So fun story, the first time I ever wrote a paper with like in this space, we had most of the results in the paper. We were getting ready to submit, and it's like, oh, we just fixed a bug yesterday. Cool, did you rerun all the tests? No, we just reran the test that it was gonna affect. like, beg pardon? They're like, oh, it just fixed this bug that affects this one case, so we ran that test again. Like, how do you know? Well, we only changed one part of the code. I'm like, we're going to rerun all the benchmarks. They looked at me like I was crazy. I'm like, why? I said, because we're claiming we have an implementation that produces these numbers, and that's not what we're showing. And they thought I was nuts. We now don't do that. We actually do run all of the benchmarks all over again, but it's not the norm in this community. Like, it really isn't. All right, so let's wrap up. I promised you superpowers. We have a bunch of superpowers that can be really helpful for people in things that are not simply making their systems run faster. Performance improvements are great. I think some of these things are actually way more impactful. And so I want to encourage you to start thinking about those kinds of problems. So, on that note, I would like to thank the NSERC, which is the federal funding agency for science in Canada. They funded all my side of the work here. I'd like to thank both ACM and 2 Sigma for the Athena Award, and of course my colleagues at Duke and UBC for this award, but most of all the amazing and wonderful students that I get to work with and the members of my team. So, thank you.
Hi, Chung Tang from Northeastern University. So, hi Margo. I think I have the same feeling as you do here, that I don't like neural network because we don't know what they learn, they're black box, whatever. But we choose a very different way, than you do. Instead of get rid of the neural network, but we try to formally verify the neural network. So I'm wondering, as a competing road of how to make this happen in systems, what do you think of that way? Thank you.
So I'm a huge fan of formal verification. What properties are you actually verifying of the neural network is what I don't quite understand.
Oh, it's going to be different for different applications. Let's use a learned index as example, for example. So we can verify that a neural network-based learned index is going to give you a prediction that is within a certain error bound that you predefine, for example.
Okay, so I think in spaces where that works, that seems great. It would, so actually, I'm glad you mentioned verification. So one of the projects that we have started, but is a bit dormant at the moment, is actually to rewrite Ghost in something like Daphne or Varus, so that in fact, what that would do is that would let us express all the math in yet another language. So we'd now have it on paper, in LaTeX, and in Varus or Daphne or whatever. But the idea is that we could actually write code that we can verify satisfies the mathematical bounds. So I actually think these aren't orthogonal problems. I think they are orthogonal problems. That verification is a great tool, and where we can use it, we should. And the kind of model you choose is a different problem. Right? And the question is, even if you can verify your neural network is doing what you want, if you could have a model I could hand you on an index card, why wouldn't you take that?
Well, we have GPUs. They run faster. I mean, neural network has pretty good filters.
I'm sorry.
Yeah.
Your TPU evaluating a neural network is still slower than my CPU adding 5 numbers.
Well, there's NPU added to CPU. But anyway, I see your point. Thank you so much.
All right. Phil.
Hey, Margo, I have a stupid question.
Thank you.
Why don't you use like a C4.5 decision tree? Why aren't they optimal? I thought they were optimal or something. Are they not?
So C4, I can talk today. C4.5 is slightly better than CART, but it's not optimal either. Binact was the first optimal. It came out about the same time we did. It's not optimal either because it does some binarization that is invalid. So at the time we did Ghost, we were the only optimal trees. There may be other competing implementations out there now, but people thought it was impossible for the longest time. So even C4.5 is not optimal, and we can show you like results that we win. so we do those kind of like we win results in papers too. Everybody does.
Hi, Joel from TU Darmstadt. So thank you for the talk. Really wonderful, wonderful talk. happy that I was here today. A question looking at the younger generation, right? So the people who are starting their PhDs now. Some of this might seem overwhelming, right? Because you want to get your footing in one topic, and I think it still makes sense. Can you just say a few words, like what's the main takeaway for someone who's, today just starting their first problem, and yeah.
So that's a great question, thank you. So the question really is like, what do you do if you're just getting started? And so I think, one of the things we try to work with young students is like, pick a very specific problem you can work on. I think the most important piece of advice I would give is be intellectually curious. Talk to people around you. As important as it is to get your project done, there is more to the world than just your project, and I think be open, be curious to people around you. I try to encourage my students to have at least, ideally one and only one side project. Like, I actually believe that it's fine to have, like, this is my work that I'm working on, and maybe I can bring some friends along who would like it as a side project, and similarly, maybe I could be a friend on their project and have it as a side project. So, maybe not your first year, at least in our program, your first year you're taking courses, you're getting started in research. That's a time to, like, focus on learning, being open to other fields, but maybe not picking up multiple projects. But I think it really boils down to intellectual curiosity, the willingness to really push and find out what other people are doing, and then waiting for the right synergy to occur where your superpower and somebody else's superpower really fit well together, right? I'm looking at two of my students who like each do each other's projects as side projects, and I think that has been really great because shockingly, sometimes projects don't go well. Who knew that? Right? And if it's not, then maybe for a couple of weeks you get to work on your side project a little more and sort of boost your morale a little bit. So I think a little bit of diversity is good. Clearly too much diversity is detrimental to finishing your degree.
Hi.
Maxim Planeta, Barkhausen Institute. So thank you for a very nice talk, and I really like that you advocate for simplicity. But my question is about Rashomon set. So I guess you find it on a training data set. How much would it change once you recompute it on the validation data set? And does it, is it important even? Would it change much of the meaning of what the model you find?
So we've actually looked at this, and I'm afraid I can't give you data off the top of my head because this is actually a project that a couple of Cynthia's students have been working on. To a first approximation, the Rashomon set doesn't change that much because what happens in the validation set is that you might find a slightly different optimal tree, but its objective is likely to be within the Rashomon set of the original, so it might shift just a little bit, but it's not likely to shift very much. The beauty of these sparse models is that the models you get do generalize well. And so there are small differences, but they're not very big.
Yeah. Thank you.
Lily, one more question. No, we have Lily who's been standing patiently at the mic. She's just more petite, so you can't see her as well.
I actually don't know whether I got here first, but Lily from MIT. Thank you so much for the talk. I actually don't think I would be asking this question if you didn't give the first part of that talk, so that was really nice. I don't know that much about machine learning models, but it seems like you're optimizing for a set data set, so the models, the decision trees that get within 1% accuracy or 0.1% accuracy. But isn't the benefit of these very complex, million feature models that they're much more flexible to adapt to unknown and unseen data? And so that would be one potential reason to use them.
So you would think that, right? But so now I'm kind of parroting Cynthia here a little bit, and I apologize, but the fundamental theorem of machine learning is that sparse models generalize better. And so, we don't find huge differences. Our training accuracy and our test accuracy are not that different. And so when you're in the right problem space, and I want to be very clear, it's got to be in the right problem space, the sparse models actually do generalize. So that means that they do predict unseen data.
Is there a mathematical or formal reason why?
Yeah, and this is this
okay.
This is this hand waving that I'm doing, but if you want the reference, I'll find it for you.
Awesome. Thank you so much.
Okay, so many student questions, but we have to finish now. And let's thank Margo again for her insightful and